classically, our GRF 5509 was the first device that got attention for RFID. We had a difficult spec with a European customer where the RFID mask is more difficult to meet. And I looked at the requirement, and 5509 seemed our best choice because it operates in the 900 megahertz frequency band. It has a large amount of small signal gain to accommodate the transceiver output. It had a high enough compression point, 4 watts, to accommodate hopefully a 2-watt signal. And we knew it was similar to former devices that we knew about in the industry. So I started working with the customer, initial evaluation board, and some linearization adjustments to the device. And we determined that it was going to require 2 GRF 5509s in parallel them using hybrid combiners to meet the mask. And we did. The part got designed in. As far as I know, it's in production at this time. And that wasn't our first RFID design win, but it was the first one that I paid a lot of attention to. Since that time, 5509 has been qualified in a leading chipset designers, manufacturers reference design. It does well. No device is perfect, but it seems to be one of the dominant PAs in the industry for the RFID application. That's really good. We're learning as we go because the RFID masks are varied in severity and difficulty by frequency band. The modes of operation are many. We're not experts. So what we've tried to do is look at a worst case scenario. If we can make our device work for the worst case scenario, it'll work for most of them. And I think that appears to be the case. So RF 5509 is in. We've learned that for lower power RFID applications, GRF 5510 works. We also learned recently that even there might even be a lower power option where we can use, I think GRF 4005 is being used. I think that even in the even lower power applications, 4014 might be in. So we have several devices that play, but 5509 is the main one. 5603 is a new one that we just started to sample for some particularly difficult scenarios, and we're going to find out very soon just how it does. What we find is the proving ground for the device is in the customer laboratory. So what little familiarity I have is we would look at the high power scenario in North America, 917 megahertz, around there. It's a 400 kilohertz mask measurement, not necessarily a 400 kilohertz bandwidth signal, but if you look at the mask, the top is a rectangle and it's 400 kilohertz wide. So that's one scenario, and I think the level of difficulty becomes evens out because you are allowed to transmit at higher power in North America, 36 dBm, I believe. But typically I'm only seeing 30 and 33. In Europe, the ETSI mask, to my knowledge, is 200 kilohertz wide, and the maximum output power there is 33 dBm or 2 watts. And and we're getting designed in. We're doing well. We have some challenges in certain instances, and we're addressing some of those right now. So we're learning a lot about that. I know that I don't know a lot about the specifics, but the mask is different in Japan. And I've had one scenario where oftentimes, typically with these masks, a lot of the challenge comes closer into the carrier frequency. I had a scenario with a Japanese customer where we were not passing the spectral mask at very large offsets far away from the carrier. I was able to suggest some biasing exercises and external termination placements that solved the issue. And I've recorded all. What I do is I record all these things in files so I can reference them, and because it's easy to forget this stuff. So yeah, the worldwide spec variation is significant, and it's going to take a while to get really familiar with all the specs and generating your own waveform in the laboratory. Building and generating the waveforms. At some point, I hope we have a handful of waveforms that we are familiar with and we can use to test with. Yeah. So, one of our first customers, one of our first major customers, combined Guerrilla 5509 and hybrid combined to get to meet their spectral mask at 33 dBm. So we suggest it. We have some customers doing it. Other customers, for cost reasons, don't want to do it. So we have to give them our best single-ended solution. I just had one customer, as a matter of fact, and the customers figure out, they come up with their own hooks. I had one customer recently who put a extremely large capacitance on the Enable 2 line, which helped with his mask. The problem with putting that big capacitor on the Enable 2 line, as you know, is it slows down your turn-on time, right? So we had to come up with a pretty ingenious way of we came up with a workaround for that. I compared 5509 and 5603 running with this waveform, showing the eval boards, showing the standard data, showing how I measure the channel power of the waveform. And it's kind of a Batman looking waveform. Here's one of the specs. See the 400 kilohertz right there? It's an Etsy spec that they called out, and I have to be under this mask here. All my spurs, all my stuff. So this is 30 dBm. 5509 on the left, 5603 on the right. 5603 clears the mask by more, but they're not dramatically different. Now, 5509 did not comply at 33 dBm. 5603 is compliant at 33 dBm. So that tells me that in many cases it's going to be superior.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.